Question 1991. A couple years ago, a College Board took out freezing point and boiling point depressions. So unfortunately, we will not be able to do Part C. And since we're not going to do Part C, we kind of need Part C to answer Part D. So I do want to work out Parts A and B because they are very beneficial. But in the future, you won't see, at least on the test or on the AP exam, hopefully not in the homework, I'll check and double check to make sure that I don't give you a question that, especially the equation is not on your equation sheet anymore for freezing point and boiling point. But we will not do Part C and Part D, but we can do Part A and B. The question reads, the molecular formula of a hydrocarbon is to be determined by analyzing its combustion products and investigating its colligative properties, which we will not be doing. Part A, it says the hydrocarbon burns completely, producing 7.2 grams of water and 7.2 grams of carbon dioxide at standard conditions. What is the empirical formula of this hydrocarbon? Okay, so again, we're looking for empirical formulas. So hopefully you're getting the idea that empirical formulas and molecular formulas are kind of important, and they are. You will see that quite a bit on the AP exam, and that'll be in May. That's a long time away from now for some of you to be thinking about the AP exam, but again, knowing what's on the exam will help you to do well on the AP exam. So we have this hydrocarbon, and this hydrocarbon has hydrogen and carbon. So we're looking for, and let's do this. We're looking for this hydrogen carbon compound, and we'll say that it's X and Y. Okay, so the information that's given to us is that it burns completely producing water and carbon dioxide. So again, that means that it's indicative of a combustion reaction, and it forms carbon dioxide and water. And we are given some information about that. So we have 7.2 grams of water. So 7.2 grams of water. And we have 7.2 liters. Let's do that again. 7.2 liters of carbon dioxide. Do we know anything about our hydrocarbon? Of course not. It wants to know what is the empirical formula for this, and it also tells us that we are at, very important, standard conditions. What does it mean to be at standard conditions? Well, if you know that, that's really going to help you out quite a bit in this problem. If it's at standard conditions, that means that we are at STP. And if you know what the conditions are at STP, life is going to be very, very easy for you. Now, what that means is if you have 1 mole of any gas, 1 mole of any gas, and we're at STP, its volume is 22.4 liters. And also, the standard temperature and pressure, and I believe it's on your equation sheet. I'm pretty sure. I'm not going to look, but I'm pretty sure. But the temperature is equal to 0 degrees Celsius, which is a bad number. We don't really like 0 degrees Celsius. But 273, we do like. And the pressure is at 1 atmosphere. Or another unit that we could use in here is 760 torr or millimeters of mercury. But probably, actually, the most important piece of information is right there. So we can find out how many moles of carbon we have because we know how many liters of carbon dioxide we have. If you worked out the previous problem, must have been 1986 that I made a video for already. We're going to use the same exact strategy to find out how many moles of carbon and how many moles of hydrogen we have. Let's go to it. So try it before you actually watch it here. And I'm going to, no, I'll leave that on there. So let's go ahead and I'm going to do the carbon first, or you can do the hydrogen. I'll do the hydrogen. So let's see here, we've got 7.2 grams of water. And what I want to do is find out how many moles I have of water, and then I'll find out how many moles of hydrogen I have. So in 1 mole of water, we'll say there's 18 grams. Yeah, 18.016. On your homework, do that. If I stop right there, it tells us how many moles of water we have, but let's find out how many moles of hydrogen, since I'm looking for the empirical formula for the hydrocarbon. So that means in 1 mole of water, I have, again, 2 moles of hydrogen. So if you didn't watch the video before this one, H2O is made up of 2 hydrogens and 1 oxygen. Okay, so we'll get a value for that here in a moment. So that's our hydrogen. And our carbon is 7.2 liters. So let's go liters, not gram. Liters, and I'm going to make this a really easy one. Conditions at STP. Now, if you want to do PV equals nRT, knock your socks off. But I'm going to use the conversion that I know that 1 mole of any gas, any and every gas at STP has a volume of 22.4 liters. So do that. 22.4 liters, and that is equal to 1 mole of whatever this is. In this case, it's carbon dioxide. But I need to find out how many moles of carbon dioxide I have. So be sure to take it one more step. In 1 mole of carbon dioxide, I have 1 mole of carbon. So let's get some numbers. So my hydrogen is 0.8 moles, and my carbon is 0.32. Oh, what's that? 0.3214. Okay. And then what I'm going to do is divide by the smallest value here. So this is one reason why I don't want to go too far out. So there's a 1, and then 0.3214. That I wouldn't just automatically round off, so let's get that value there. My calculator says 2.4888 repeating, which is very, very close to 2.5. Okay? We wouldn't look at that and say, oh, 2.488 repeating is, we'll bump that up to 3. Don't ever do that. Make sure that you, when you're doing, and again, if you need to review the video that I made for empirical formulas, when they're not exact values, they're very, very close to 0 or very, very close to the next number moving up, make sure that you use fractions. So I took my 2.48 repeating and made that closest to 2.5. Now recall that we want to multiply by the value that's in the numerator, the denominator, We're going to multiply that value by 2 for everybody to get rid of that fraction. It means I have 5 of those and 2 of those. So when looking at this, my formula for my hydrocarbon is that I have 2 carbons and 5 hydrogens. So the way I should write this is, carbon generally goes first. So I have 2 carbons and 5 hydrogens. Okay. And that is part A. And again, there is more than one way to work these problems out. And just as long as you're showing all your step and all your work, it's okay. All right, so let's look at B. It says calculate the mass in grams of oxygen required to complete the combustion of the sample of the hydrocarbon described in A. So let's see here. We have our hydrocarbon, so let's write that down. C2H5, and we're reacting it with oxygen to form carbon dioxide and water. Okay? Very important here. Do we know some information here? We know that we want to know calculate the mass in grams of oxygen. Okay, so we're looking for the mass of the O2. Actually, let's scoot all this down. So we're looking for the mass of the grams for our carbon dioxide to be completely combusted. Let's assume that we have 1 mole of this. Actually, let's make sure we do this correctly. Let's balance this formula out. So again, let's do this is a stoichiometry problem, so balance out the equation. I'm going to start off, since I have an odd number of hydrogens here and an even here, I'm going to go ahead and start off by putting a 5 here. Actually, choose a different color. A 5 here. Okay, so that gives me 10 hydrogens, so if I put a 2 here, That gives me 10 hydrogen, and I have an even number of oxygen. I do not have an even number of oxygen, so I need to change that 5 to an even value. So let's do that. So I am not happy with an odd number. So a value of, or a multiple of 5, multiply that by 2, then I get that. So that means I need to change this to a 4. Okay. And now my hydrogens are balanced. I have an even number of oxygen on the right side. So I have 8 there, so let's put an 8 there. Okay. And let's see here. We know that we have some information about carbon dioxide. Actually, let's go with water. 7.2 grams of water is produced. Okay. So let's go red on that. So from this reaction, we know that we have 7.2 grams of water produced. Okay. I think we may have everything that we need here. So let's do that. Okay. So we know that's all we need. So we've got our balanced equation, step 1. Step 2, let's change what's given into moles. So we'll start off with what we know. We have 7.2 grams of water. And we'll change that into moles. So 1 mole of water is equal to 18.016 grams. Notice how I get really specific now. And then I'm going to do a mole ratio, get rid of the moles of water. So moles of water compared to moles of oxygen. I don't think I finished balancing this. Hold on, let's finish balancing. So I've got 16 plus 10 is 26, so I got a 13 here. Okay, kind of need that value for this next step. So that is 10 waters and 13 oxygens. So step 1, change what's given into moles. Step 2, use the mole ratio, get rid of the moles of water to get the moles of what we're looking for. Since it's asking for mass, let's change that into mass. Okay. So 1 mole of oxygen has a molar mass of 32 grams, or 2 times 16. And let's find out how much oxygen is required. 16.7. I have 16.7 grams, and that is oxygen. That's right. All right, so, and again, you have to realize that when you're working these types of problems out, you have to know what you're given and what you're working with. Unfortunately, I really wish that we could work out C and D, but I don't want to spin your wheels. We will come and do another problem where we actually find the molecular formula, and you'll have many opportunities to do that in the following questions as well. But make sure that you're using what's given. In this case here, the 7.2 grams of water was really helpful in helping us to solve the problem in regards to how much oxygen was used.